let's take a look at our next question. And in this question, I want to answer for you, what is a generator really? How is it related to functions? How is it related to lambdas? How is it related to generator expressions? What are the underlying mechanics of the Python generator? Let's take a look. One important thing to remember when you look at Python is, irrespective of the confusion that I introduce around whether something is a coroutine with a lowercase c or a coroutine with an uppercase c, which is a completely made-up distinction that I made up just to reconcile how we used to talk about things in Python back in the day, and how we talk about things in Python now, fundamentally, a lot of things aren't really what they're called. There is a distinction, or at least there's a break between how we refer to certain things casually and what they actually are referred to by the Python interpreter. So, for example, if I asked you what WISE is, you would say, well, WISE is a list comprehension. But I might say, no, WISE is a list that was created via comprehension syntax. And I know the moment I say that to you, your eyes are rolling and you're just like, come on, you get what I mean when I say WISE is a list comprehension. Okay, I buy it. WISE isn't a list. It's a list comprehension. We'll say that the clarity that we introduced by saying it's a list that's created via list comprehension maybe is being a little bit too specific. If we look at f, we might ask, what is f? And clearly f is a function. And if we ask Python what f is, Python will say, yes, it is this function type. And it'll even say more broadly, it is a callable. It's something that you can put open close parentheses. So I'm not quite seeing where things aren't what they're called. I don't quite see the break in our terminology and how things are actually implemented. If I take a look at f and I define it in this fashion, we can see that from Python's perspective, this is a function, it's a function type, it's a callable like any other. In fact, Python doesn't really maintain any distinction between the function defined with a def and the function defined with a lambda. There's maybe one or two small distinctions if you dig deep enough in terms of what you can find, what you can pull back out, but for the most part, these are effectively equivalent. So here, you might call this a lambda, but it's really a function that was created with lambda syntax. Okay, don't quite see the distinction just yet. If I ask you what G and GI are, you're going to tell me that G is not a function, it's a generator, and GI is a generator instance. But this is not what Python calls them. G is a function to Python, and GI is a generator. What you and I call generators, Python actually calls functions. And what you and I call generator instances, Python actually calls generators. And if we ask Python which of these is the generator, Python will tell us that what we think as a generator instance is actually to Python the generator itself. This is not a generator to Python at all. This is not what we call it, but this is what the Python interpreter refers to this thing as. And if we go a little bit further and we think about not just generators, but coroutines, things which we can send input back into, we might say, well, clearly, this is maybe a function and this is a coroutine instance, or this is a coroutine. Typically, we call this a coroutine and we call this a coroutine instance. But Python again says this is a function and this is a generator, and neither of these are coroutines. It's only this latter one, that what we call a generator instance, that is a generator object. If we go into our async IO and we ask Python, what is this? And we might call this an asynchronous coroutine, or a coroutine with a capital C, or an asynchronous task, or whatnot. We ask Python, what is this thing? You know what Python's going to tell us? It's going to tell us, this is a function too. All of the things that we see which have def in them, to Python, they're just functions. And Python doesn't actually make a distinction in terms of the types of these things or what Python calls these things at that level. If we ask Python what happens when we invoke this thing, it says this is a coroutine. So Python says the result of calling the function that's defined with async def is a coroutine, which is not even close to how we refer to these things. And if we call await on this to get this awaitable object, and we see what type we have here, we get a coroutine wrapper, which we don't even refer to. We don't have a word to talk about this. Nobody ever says, oh, is this a coroutine wrapper? If we ask Python whether these things are awaitable, Python says only this thing is awaitable. And if we ask Python whether these things are coroutine, Python says only this thing here in the middle is a coroutine. But this kind of makes sense to us. Python's terminology here is based off of the protocols. Python's saying, you know what, anything that has a call method implemented is a callable. And in fact, Python's not even that picky. Note that this first thing that I've defined here does not have a call method implemented. It just has an attribute called call. But Python says, well, it's a callable because, you know what, it's going to say, you know what, if this is not really valid, but I'm going to let you wait until runtime to figure out that this is complete garbage. This is just an ellipses object. It's not an actual function. If we ask Python what a generator is, Python's going to say as long as you have an iter, a next, a send, a throw, and a close, as long as you implement those parts of the protocol, I consider you to be a generator. Therefore, Python doesn't say that the def with a yield in it is a generator. It says the consequence of the def with the yield in it is the generator, because what it thinks of the generator is something that implements the generator protocol, which is only, in the case of a generator, the generator instance. Similarly, an awaitable is anything that implements the awaitable protocol. And similarly, the coroutine with a capital C is anything that implements the coroutine protocol, anything that's an awaitable and has a send, a throw, and a close. Now, I don't want to go any deeper into this, what an async iterable is or an async iterator is, but I want to show you something important. When you look at this structure here, you might say, what is this? Is this a tuple comprehension? No, there's no such thing as a tuple comprehension. Is this a generator? Is this a generator instance? Well, here we can see that what G is the generator object. This is the actual generator itself. What I want to show you out of all of this is Python's internal conception of what these objects are really ties to the underlying protocols that are implemented. Python says that the consequence of this generator expression syntax is a generator because this thing implements the generator protocol. It implements send, throw, close, next, and iter. And where we see this distinction in terminology is really, are we talking about the entity that we've coded and our understanding of how that entity fits into the design of our program? Or we're talking about the mechanism that operates under the covers that implements certain protocols that satisfy the Python interpreter? Well, when we think about the intersection between these two areas, the design and the implementation, one thing that we might think about is necessarily in order to implement generators and asynchronous tasks, there's a level of indirection, and necessarily the reason why we use asynchronous task generators is to make use of that indirection. Here's what I mean. When we have a function and we invoke that function by putting open close parentheses after it, we get the result immediately. There's no indirection between the entity that represents the computation and what happens when we put input data in and we get some input data out. However, when we deal with a generator, as we would call it, some def-defined thing with a yield in it, there's an indirection. When we call the generator, it gives us the generator instance, or what Python calls generator object, and we have to ask that thing for the corresponding values. There's an indirection. We call something to get something, which we then ask for the output values. And so there's one step of indirection between what we invoked and the thing that gives us the outputs. This indirection, in the case of the generator, represents the computation. When we call this generator, we get a representation of the computation, what you might call a thunk, and then we ask that thing for the next state of the computation, the next step of the computation. And it's the same thing in our asynchronous world. Here we have an asynchronous task. When we call this asynchronous task, we get the representation of the task, we get an indirection, which we have to generate an awaitable from, or which we then have to iterate over in order to actually perform the computation. There's levels of indirection here. Bear in mind that when we think about it in terms of levels of indirection, we think about it in terms of what these things are called. A correspondence does arise for us. What we call a generator, a function with def and yield that produces what we call a generator instance, is actually strictly equivalent to a lambda that creates a generator instance via the comprehension syntax. Here we can see a strict equivalence. Any generator that's written in this fashion can be written in this fashion as long as it can be expressed in terms of the generator expression syntax. Now, one of the things that I want you to think about as we now dive even deeper into how generators are actually implemented is the implementation of generators in Python is actually relatively simplistic in the sense that it's just an extension of function behavior. Remember, when we look at F, G, and T here, from Python's perspective, all three of these are just regular functions. It can't even tell that one of these is different than the other, at least in terms of the type. It can tell that there is a difference when you execute these because there are flags that are set. When we define a function with def and we don't put a yield in it, when we define a function with def and we put a yield in it, when we define a function with async def and we don't put a yield in it, and when we define a function with async def and we put a yield in it, well, we get entities that all look very similar, but when we dig a little bit deeper, these are actually functions with different flags that have been set that affect how the C interpreter is actually going to execute these. Let me show you what these flags correspond to by asking the dist module to tell us what these flags correspond to. Here, we can see a regular function just has a couple of flags, just referring to whether it has free variables, whether it has, whether it can be optimized or whatnot. G has a special flag indicating that it is a generator. T has a special flag indicating that's an asynchronous task, a coroutine. And AG has a special flag indicating that it's an async generator. Here's what actually happens behind the scenes. When we call a function, we execute the main evaluation loop in the Python interpreter, and we just go through the bytecode from top to bottom. When we execute a generator, we go through that main evaluation loop from top to bottom until we hit a yield value, and then we execute that main evaluation loop. Let me show you what I mean by actually showing you the C interpreter code and the main evaluation loop in Python. When we have a yield value, actually, let me work backwards. When we're evaluating the bytecode in Python, what happens is we have a gigantic for loop, or what historically has been implemented as a gigantic for loop that just says, what's the next instruction? Go and switch to that next instruction. And you can see we're switching to the different opcodes. You can see all the different opcodes. You can see load fast, load constant, binary multiply, unary positive, whatever the case may be. And we're switching between these. Historically, this was implemented as an actual infinite for loop, but now they have these computed go-tos. So whenever you see this dispatch, this thing here is actually a go-to. If you dig through this thing enough, you'll see where this thing is defined, and you'll see this is actually an actual C go-to statement that goes to the top of the loop. So it's basically an infinite loop. This one function represents how we implement the execution of any bytecode in any function. When we get a yield value, a special thing happens. We return out of this function. Basically, generators in Python and functions in Python are implemented in exactly the same way. They're just streams of bytecode that you go bytecode, dispatch, execute, bytecode, dispatch, execute, bytecode, dispatch, execute, except in the generator, you've set a special flag that indicates that you're able to suspend this thing, that you're going to potentially resume this thing. And when you hit the yield value, you actually return out of this. You pretend that the function has completed running. That special flag is necessary to set up a little bit of state behind the scenes to allow you to keep all of the information that's related to the current run of that function around so it doesn't get deallocated when you return from this. A Python generator is just a function that you can return early from in the execution of the bytecode that keeps its state of the computation around until you resume it. And it has a couple of things like these GI state. It has a little bit of internal details and bookkeeping to support this. When we run a Python generator or a Python function, we can see that there's a current frame associated with this. This is the storage for that function, all the local variables and the state of those local variables. And we'll see it in both the cases of the function and the generator. The difference is when we have a generator, we don't run this function to completion. We run it to a specific bytecode, but we keep around the instance or the state of the execution so that we can resume this. So what will happen is, if we were to do 3 nexts through this generator, next, we'll see that in that special bookkeeping, we keep track of the last instruction that was run. And you can see that every time we hit this yield value, the generator is in its bookkeeping just saying, you know what, I've run this function up to this bytecode. I returned out of the evaluation of this function. But when you come back into me, I'm going to resume from this bytecode. Then I'm going to run up to this bytecode. You can see that's what this 10 is. Then I'm going to run up to this bytecode up to the 16. What you can think is, Python generators are actually just generalizations of how functions. They're just functions that allow you to pause when you had a yield and resume from that yield point, and they just have a little bit of bookkeeping associated. That's why you can't distinguish between the Python function and the Python generator without looking at those flags, because from an implementation perspective, they're identical. And what you can think is that level of indirection is just giving you some object which represents the runtime state of that function that just gives you all of the bookkeeping and a way to access that bookkeeping, a way to go back into that execution of that function, picking up where you last left off. When we talk about coroutines, that is, generators would send, we often talk about them as generalizations of functions. When we talk about them as generalizations of functions or subroutines, we talk about that from a semantic perspective, from a conceptual perspective. In other words, a subroutine is something that takes input, does some work, and gives output. A coroutine, a generator would send, is something that takes input, gives you some partial output, takes some more input, gives you some partial output, takes some more input, gives you more partial output, and so forth and so on. But it turns out that under the covers, the coroutine or the generator the non-asynchronous version, the thing that's defined with a definite yield, is in fact implemented as a generalization of the Python function. It really is just some Python function with a special flag that tells you, I'm going to allow you to return early once you hit a special bytecode, and I'm going to give you a representation of some entity that allows you to resume from that point and keep going. That's all a generator really is under the covers. The implementation is quite simple, and I might even say quite elegant.